So, have you ever stopped to think about something super basic? When you've got a list of things on your computer, how does it actually store them? I mean, really deep down. It sounds simple, right? But the answer? Well, it's this amazing story about speed versus flexibility and some really clever trade-offs that happen under the hood.
All right, so let's get right into it. When your computer needs to keep track of a list, like your favorite songs, the contacts in your phone, even just the letters you're typing in a document, it really boils down to two classic approaches.
And that brings us to our two main characters for today, the array and the linked list. Seriously, you can think of them as having completely opposite personalities. The array? It's all about order. It's rigid, everything in its place. The linked list? It's flexible, a little more scattered. And it's this clash, this tension between them, that makes this whole topic so cool.
Okay, so first up, let's talk about the array. And honestly, the best way to get your head around an array is to imagine a street of houses, but like a perfectly planned, super neat street.
And the key word here, like the one word you really need to remember, is contiguous. That just means everything is stored right next to each other in one unbroken block of memory. Just like on our street of houses. You've got house 1, then right next door is house 2, then 3, no empty lots, no gaps, it's all one continuous block. That is the array's defining feature, its whole identity.
So you might be thinking, why be so rigid? Well, here's the payoff. Incredible, mind-blowing speed. See, an array doesn't have to search for anything. It calculates the exact address. The computer knows where the street starts, that's the base address. It knows how big each house is, that's the element size. So if you say, hey, get me the 50th house, it doesn't walk past 49 houses. It just does a tiny bit of math and bam, it jumps directly there, instantly.
And that, right there, is the array's superpower. In the programming world, we call this O of 1 access, or constant time access. It's a fancy way of saying something really simple. It doesn't matter how big the list is. The time it takes to find something is always the same. You want the first item? Instant. You want the millionth item? Also instant. The size of the list just doesn't slow it down. It's amazing.
But wait, there's more. There's this awesome bonus feature. Because all that data is packed together so tightly, it's fantastic for the computer's processor, specifically its cache. Just think about it like this. It's way more efficient for a mail carrier to deliver to a whole block of houses at once than to drive all over town, right? Well, the CPU is the same. It can just grab a big chunk of the array's data all at once. Super efficient. We call this locality of reference.
Okay, so this all sounds perfect, right? Fast, efficient, what's not to love? Well, this perfect, orderly street, it has a huge problem. It was never designed for renovations. And this is where that rigidity we talked about, well, it comes back to bite us hard.
So what happens when you want to build a new house right in the middle of the street? Let's say you want to squeeze one in between house number 5 and house number 6. What do?
Remember, on our perfectly contiguous street, there's no empty space. So to make room for just one new house, you have to shift everything after it. You literally have to pick up house number 6 and move it down, then house number 7, then 8, all the way to the end of the street. It's this massive, incredibly expensive construction project. In computer science terms, we call this an ON operation, or linear time, and that N is the number of houses you have to move. So the bigger the list, the more painful the insertion. The big takeaway for our arrays is looking things up is super cheap, but changing things, that can get really, really expensive. And that massive renovation problem is exactly why our second character exists. Enter the linked list. It was specifically designed to solve this issue, and it does it by using a completely different model. So if an array is a neat street, a linked list is more like a treasure hunt. Each piece of data, we call it a node, can be stored anywhere in the computer's memory. It's totally scattered. But each node holds two things, the data itself and a crucial clue, a pointer, which is just the memory address of the next node in the list. So they form this chain of clues, but the links of the chain can be spread all over the place.
And this is where the linked list really shines. Look how easy it makes that insertion problem. You don't have to move anything. You just create your new node, and then you just sort of rewire the clues. You tell the node before it, hey, your next clue now points to this new guy, and you tell the new node, okay, your next clue points to the one that used to be next. That's it. Just a couple of pointer changes. No massive data shifting. It's an O1 operation. Just beautiful flexibility.
This flexibility makes linked lists absolutely perfect for things where you're constantly making changes. The classic example is a text editor. Think about it.
Every single time you type a letter in the middle of a sentence, you're doing an insertion. If your editor used an array, it might have to shift the rest of the entire document over for every keystroke. That would be insane. A linked list handles that kind of thing beautifully.
Okay, so the story seems pretty simple so far, right? If your list doesn't change much, use an array. If it changes all the time, use a linked list. Case closed. But not so fast. Modern computer hardware throws a massive wrench into this whole story, and it reveals some hidden costs to all that flexibility.
So we've got to ask, for anything with lots of insertions and deletions, the linked list is the clear winner, right? Well, on paper, in theory, yes. But in the real world, it's a lot more complicated.
And this really gets to the heart of it with this fantastic quote from a discussion on Stack Exchange. It says that the hardware we use today is very fast at moving large chunks of memory around. In fact, our processors are so insanely good at that expensive task of shifting data that it can actually be faster than the seemingly simple job of following a bunch of pointers scattered all over the place.
This whole problem has a name. It's called pointer chasing, and it's the linked list's hidden weakness. If you want to get to the 50th item in a linked list, you have no choice. You have to start at item number 1, follow its pointer to item 2, follow its pointer to item 3, and so on, 49 times. You're just jumping all over memory. That's an O of N operation for just finding something, the total opposite of an array's instant access.
And remember that locality of reference that made arrays so great? Well, pointer chasing is a nightmare for it. The CPU's cache becomes totally useless. In fact, modern CPUs are so smart they even try to guess what you'll need next and load it ahead of time. It's a cool trick called prefetching. It works perfectly with an array because the next item is, well, it's right there. But with a linked list, it's impossible to guess. The next clue could be anywhere. The CPU is back to that mail carrier who has to drive to a different neighborhood for every single piece of mail. It's just slow.
So, where does all this leave us? It seems like both have major pros and cons. And that's the point. Like so many things in computer science, there is no single best answer. There's only the right tool for the job. It's all about appropriateness.
Okay, so this table really lays it all out. You'll see this theta symbol, which is just another way of talking about typical performance, like the O notation we used earlier. And look at this. For access, the array is a clear winner with that theta 1 speed. For insertions in the middle, the linked list wins with theta 1. But see that little asterisk? That's the catch. It only works if you already have a pointer to the right spot. And down at the bottom, memory locality, arrays are excellent, linked lists are poor. And that right there can be the deciding factor.
So here's the rule of thumb, the big takeaway. You should probably reach for an array when you need fast, random access, when you're going to be reading data more than you're changing it, and especially when performance really matters because of that memory locality. On the other hand, you'd use a linked list when you know you're going to be doing a ton of insertions and deletions, when the list size is unpredictable, and when that cost of pointer chasing is something you can live with.
And there you have it, the story of arrays versus linked lists. It seems like such a simple academic choice, right? But it's actually this deep, fascinating engineering decision. It's about balancing what's elegant in theory with what's actually fast on real modern hardware. And these fundamental choices, these building blocks, they are absolutely everywhere in the software you use every single day. So the next time an app feels incredibly fast, or maybe your program just stutters for a second, you might just be feeling the ripple effects of one of these invisible choices, a decision made a long time ago between a perfectly orderly street and a scattered chain of clues.